In this recording, we're going to learn about exponential decay. Okay, so that could happen when you have a consistent rate that the function is decreasing by. Okay, so it occurs when a function decreases by a consistent rate. So that's kind of the opposite of exponential growth. We're not decreasing by a consistent amount. That would just be a negative slope on a line, right? But this is a multiplier that causes the initial amount to decrease. So let's use an example here. You may actually do this if you have a piece of paper. A standard piece of paper is 11 inches by 8.5 inches. So if you want to take a piece of paper and cut off half an inch and then cut off 3 inches, you would have right in here an 8 by 8 sheet of paper. Right? So you could actually do this. If you don't actually do it, you can imagine. All right, I have an 8 by 8 sheet of paper. What's the area? So go ahead and answer questions A, B, and C. Play the recording when you're ready. Okay, so if you identified, you'd have 64 square inches for an 8 by 8. If you ripped it in half, well, you'd have half of that, right? So 32 square inches. Rip it in half again, you'd have 16 square inches. So continuing that process, I'd like you to complete this table until you run out of space. Play the recording when you're ready. Okay, so hopefully you got the following. All right, so now in terms of graphing this, we'll consider that to be the x, the number of rips. And you can see that it gets smaller and smaller and smaller, but we're not going down by a constant amount. It's times half, times half, times half, times half. So it's a multiplier that causes us to decrease. So if we call this the y-axis and the x-axis, like we commonly do, think about a scale that will accommodate on the x-axis the 0 through 7. I'm not sure why we set it up like this with the big axis in the middle, right? Because really we just want the first quadrant. We're not talking about any negative amount of rips or negative area of paper. So really the first quadrant's the place we're going to do all our graphing. So set up a scale on your y-axis that will accommodate all these y values as well. Play the recording when you're ready. All right, so I'm going to go by tens on the y-axis. We go by ones on the x. Having done that, let's plot these points. You're going to have to estimate approximately where 64 is, the less than halfway up the box, and so on. Okay, at that point, it's pretty tough to distinguish between 2 and 1.5, right? And now you might have already connected these, and that would be the question. Do we connect these dots and make it a continuous graph, or do we just leave them as discrete points? If you remember, we've talked about this before, and the answer lies in whether or not there's meaning for the points in between the points we've plotted. In other words, in between the 0th rip and the first rip, is there a half a rip that would give me some meaningful number in terms of an area of paper? Is there a 0.375 and all the other real numbers that exist between 0 and 1 that would result in a meaningful y value? I think we can see that, no, that doesn't make any sense. So just leave them as discrete points. Now in terms of like a pattern here, hopefully you noticed a pattern, right? You do have a starting amount, and what are we doing to that amount each time, right? Multiplying it by half, or 0.5. I'll write half here. multiplying it by half. We keep just taking half, right? Multiplying it by half. So if I wanted to get down to the fourth rip, how many times would I have multiplied by half? I think we can see that it's 4 different halvings, right? So to get to the fifth one, I would have multiplied by half 5 times. Again, the way we represent continued or repeated multiplication is an exponent, right? So if I wanted to get to that fifth one, it would be like, let me just draw a little arrow over here. That one would be like 64. You started with our initial amount of paper, and we're multiplying by half 5 times, right? That's our exponent. So let's use that information a little bit as we develop a formula. So similar to our exponential growth formula, we have an exponential decay formula. We have an amount that we're generating. We start with our initial value, our principal, and we have a decay factor, a number we're multiplying by each time. And instead of being 1 plus the rate, it's actually 1 minus the rate each time. We'll talk a little bit more further as we look at the more sophisticated examples. The half can be a little misleading because 1 minus a half is half. We'll have to look at some other examples. And we're going to do that t amount of times. So A is our amount after time t. Okay, t is often measured in years, but it doesn't have to be, right? It could be rips. So we can't really talk about t years. So let's just jump down to here. T is the number of multiplying factors we did, the amount of times we sent it through, and it's often years. Okay. P we said is the principal. Or initial amount. R is the rate of decay. As a decimal. So again, coincidentally, because we were taking half each time, 1 minus half, the base was half, but if we were taking, I don't know, some other thing, a quarter each time, it wouldn't be a quarter as the multiplier, it would be 1 minus a quarter, right? And so we'll have to be precise when we do that. So we know how many square inches we expected after 3 rips. According to our table, it's going to be 8 inches squared. So let's see if our formula results in the same value. So we'd say A equals our initial amount. So we start with 64 square inches. 1 minus half, which is going to be half, as we talked about, raised to the 3rd power, because we did that 3 times. Let's just keep coming back to our table here, because I think this table made a lot of sense to you. 1, 2, 3 times we multiplied by half. That can be written as an exponent, half to the 3rd, as long as I have it in parentheses. You could have also done a 0.5 to the 3rd, right? So let me just crank this out. 64 times half to the 3rd. Pop that into the calculator. Turns out it is 8 inches squared. Well, our table didn't extend out to 11 rips. Let's have you find out the amount of area after 11 rips. Then please play the recording. Okay, so hopefully you've paused. We're going to have to grab our calculator to find that out. I don't know half to the 11th off the top of my head, but we'll do 64. And then you can just put in 0.5 if you don't want to go fractional. Raised to the 11th power. So 0.03125 square inches. So I'm going to skip this example too. But I guess I would ask you, at what point will it ever be nothing? Will I ever have no area at all? Do you think that would be possible, or will I always have just a little bit? So that's something for us to ponder as we talk about exponential decay. Will I ever reach 0, or will I always just have a half of a smaller amount, right? So a smaller and smaller value. Okay, looking at example 3, I'd like you to read this question, underline anything you think is important. Play the recording when you're ready. Okay, so hopefully you paused and you pulled out the important facts, like, okay, we're starting with $20,000. That's how much he invested. Company's not doing well. The money is decreasing at a rate of 8% per year. And we want to know, okay, what will it be in 9 years? So I think as we start to pull out the pieces here, we can identify the initial amount. Remember, that's called the P. The rate, okay, and it's decreasing, okay, so that's important. So we know we're going to be doing a 1 minus R, right? We're not growing. The R is 0.08. T is 9. So now we can set it all up. Why don't you set it up, enter some numbers in your calculator, and play the recording when you're ready. Okay, so hopefully you get your initial $20,000 times 1 minus 0.08. Raise that to the 9th power. So it's really getting 92% of its previous year's value, because when we do 1 minus 0.08, we're left with just 0.92. Let's put some numbers into our calculator and find out what it is. All right. I'm going to do 1 minus 0.08. I could have also just done 0.92 raised to the 9th power. So that $20,000 that they invested is now less than half. It's $909,443.23. Okay, so that's the power of exponential decay, is it allows us to quickly jump to a particular amount of time that otherwise would have required us to do repeated multiplication. Instead, we can use an exponent and get to that result pretty quickly. Thanks for watching.